Good morning, everyone, and thank you for joining us. My name is Yakir, and we are going to talk about how we are counting unique users in real time. Let's see. So together with me today is also Itai, who is the tech lead for our big data group, and we are both working for a company called Nielsen, and more specifically for a unit called Nielsen Marketing Cloud. For those of you who don't know Nielsen Marketing Cloud, it is based on the acquisition of a startup company called Excelate 4 years ago. We are a data company, which means that we get huge amount of data from online and offline sources. We are dealing with the device level data. Device can be a smartphone, tablet, smart TV, etc. And for every such device, we are building a profile. In our case, profile is just a collection of attributes that we assign to every device. So for example, we can decide that a specific device is being used by a male from United States, also interested in sport and driving a sports car. For doing all these insights or attributes generation, we are using many machine learning models. And at the end, our clients can use all the data that we generated for getting better business decisions and also for targeting use cases, so we allow them to target specific devices on the web. Okay, so for supporting all the things that I just described, we have this architecture here. Everything starts with our front-end layer, which collects or gets the offline and online events. We are talking about more than 5 billion events every day. The front-end layer is responsible for doing the basic enrichment. So this is where we generate all the different attributes and assign the attributes to the devices. Then, through Kafka, we are sending all the data to our backend layer or to the big data layer. There we have Spark and Flink applications that pulls all the data from Kafka. We have different ETLs to read the data, do some initial processing or additional processing, and then put the data in one of the data stores that we are using. We are using Druid, Clastrix, Snowflake, and many more. On the backend layer, we also have ETLs that are training additional machine learning models. We have ETLs for pushing the data to our data lake. So many things happen on this layer. And then we have the third layer, which is the applications layer, where all this layer consists of the different applications that are being exposed to our clients. So these applications use the data that we stored in the previous layer on the data stores to serve the different queries that we get from our clients. Okay, so at Nielsen Marketing Cloud, there are basically two types of questions that we try to answer. The first question is a uniqueness question. So we need to know how many unique profiles or unique users of a certain profile we have, or we can reach. So for example, if our client wants to run a campaign for young women who love tech, so we can specify the different attributes for this campaign. So for example, he's looking for all the devices that are being used by female in this specific age with this annual salary, live in the United States, and also tech enthusiasts. And we need to find, in real time, the number of unique devices that match this criteria. The second type of questions that we try to answer is the simplest one, is just how many impressions a campaign received. So if our client wants to measure the exposure of a campaign, we should be able to give him the number of impressions. Okay. So to give you an example to one of the screens that we have in our system, this is a screen that we call the audience builder. Audience in our world is a combination of attributes that the client can define. So if we will use the previous example of women who love tech, the client can drag the different attributes that define this audience from the bottom of the screen to the upper part. In addition, he should define the relation between the attributes. So you can see that here is defining the end relation. So we are taking the tech enthusiast female in this specific age. So this is the relation between the different attributes. And our task is to show in real time or calculate in real time the number of unique devices that satisfy this formula. So for now, let's focus on the uniqueness question. And if we will try to generalize the questions that we try to answer, so we are looking to answer the following question. How many unique devices we have over some date range? It can be any date range in the last year, and for a given set of attributes, any combination of attributes as we have seen before. And our task is to find the number of distinct elements or the distinct device IDs that we have in the stream that match to the criteria that the client specified. Okay, so we are talking about the count distinct problem, and as you probably know, there are a few possible solutions to this problem. The first solution, which we call the naive approach, is just to store everything. So let's say that you have a stream of events. You can identify every event by a device ID of the device that generated this event. If you want to know the number of unique devices you have in the stream, you can just go store all the different device IDs that you've seen so far. Every time you get a new event, you check whether this is the first time you saw this ID. And if not, you add this ID to the set. At the end, once you want to count the number of unique devices you have, you just go over the set, count the number of elements you have in the set, and you basically get the number of unique devices in the set. So this method is not very efficient, but because it requires a lot of storage. You need to store the device ID. And in our universe, we have 10 billion devices, which you can end up using a lot of memory. And also, the time complexity is not great because you need to scan the entire set in order to find the number of unique devices. A better approach, at least on the storage aspect, would be to store only 1 bit per device. We call this approach the bit vector approach. And this approach is being used by some systems today, like Elasticsearch and Redis. So in this approach, you don't need to store all the device ID. You store only 1 bit. Now, if you think about it, what we need to know is just whether we have seen the device or not. So we can represent the answer to this question as a bit flag. And let's say that we have 10 billion devices, so we can store a bit vector with 10 billion bits. And then whenever we see a device ID, we just turn on the relevant bit. At the end, once we want to know the number of unique devices we have seen, we just go over the bit vector and find out how many bits are turned on. So this approach is much more efficient, as I said earlier, in terms of the storage required. For our universe with 10 billion devices, you will have to store only 1 gigabyte per day, but it gets more complex. And this is because we have 80,000 different attributes, and you need a bit vector for every attribute. So you will end up with more than 100 terabytes every day, and you can understand that it's not very scalable. So luckily, there also exists a third approach, which we call approximate or estimate. And we will deep dive into this type of methods in later slides. In this type of solutions, you don't get the exact number of unique elements. You get some estimation, which should be close enough. But in return for the loss of accuracy, you get significant improvements, both on the storage required for the solution and on the time complexity required for the solution. So we are dealing with the count distinct questions for a few years now, and historically we started with Elasticsearch. With Elasticsearch, we had 2 big issues. So the first issue was that for indexing only 250 gigabytes of daily data, which was only part of our data, the indexing process took more than 10 hours to complete. So it was very slow. But the biggest problem with Elasticsearch was that during this time, when the cluster was indexing the data, the cluster was very unresponsive. So even simple queries took more than seconds to complete. Now, the second problem that we had was around querying the data. So in general, the level of concurrency or the amount of concurrent queries that we could run in parallel on the cluster was very low. And in addition to that, because of the way we structured our cluster, every query had to scan all the different charts of the index, which resulted in very slow queries. So just to give you like a basic sense of the performance that we could get out of Elasticsearch, you can see that as the number of concurrent queries went up, the average response time in millis went up even faster. And you can see that for a relatively low amount of concurrent queries, like 100, the average response time was more than 2 seconds per query. So at this point, talking about almost 3 years ago, we understood that we have a problem. The Elasticsearch solution is not working, and we need a better solution. So we tried something else that we called pre-processing. If you remember, we are looking to serve the different client queries that consist of the combination of attributes and the date range, and we need to calculate in real time the number of unique devices that we have for this combination. So we said, why not just pre-compute all the different combinations that we have, find the number of unique devices we have for every such combination, store it somewhere, let's say in Redis or something like that, and then whenever we get a query from the client, we just go to Redis, pull the number for the right combination, and show it to the client. This sounds really simple. The only problem was that in our case, we have just too many combinations. We are talking about 80,000 attributes, any date range. So we couldn't just calculate everything, all the different combinations. So we had to move ahead and find a better solution. So then we started to investigate something that is called statistical algorithms or approximation algorithms. In these type of algorithms, you don't store all the elements as in the bit vector approach or in the naive approach. You just store a sample of the elements in the set. And as I said earlier, you get an approximation of the number of unique devices that you have. And the first algorithm that we tried was called, or still called, hyperloglog. So we started with hyperloglog because hyperloglog had Elasticsearch had really great out-of-the-box support for hyperloglog. So this is why we decided to start first with this algorithm. The big problem with Elasticsearch and hyperloglog was that all the computations or all the processing for the hyperloglog algorithm was being done during query time. So the queries were still pretty much slow. So then we moved to a better algorithm, at least in our opinion, which is called Theta Sketch. Theta Sketch is a generalization of the KMV idea, or the KMV algorithm. And for those of you who don't know KMV, it stands for K minimum values. This is another sampling, approximation, or a statistical algorithm, you name it. And with this algorithm, you can estimate set cardinality. So it basically means that you can get the number of unique elements in a set or in a stream. I forgot to mention, but K defines the number of elements that you store in your sample. So this is a constant that you should define. And minimum values refers to the process of selecting the elements to the sample. Now, the biggest benefit for us with Theta Sketch or KMV was its great support for set theoretic operations. So we could calculate the union between two sets, the intersection between two sets, without losing too much accuracy. The only problematic case that we found with KMV was when we tried to intersect a very small set with a very big set. And Itai will later show you how we managed to overcome some of these issues. And now to give you like a short or basic intuition test to how KMV works behind the scenes. So let's say that I have people standing in the line. And I know the line length, it's 100 in this case, and I want to estimate the number of people standing in the line. So one approach is to just take the line length and divide it by the average distance between every couple. But we want to demonstrate the KMV process, so we won't use all the distances. We will start with k equal to 1. So we need to take the minimal distance. So in this case, it's going to be 5. So if we take 100 divided by 5, we will estimate that there are 20 people standing in the line. Now, you can count by yourself and see that this estimation is not really good. So let's see if we can improve the estimation by taking a larger k. So let's try with k equal to 4. So we'll take 5, 10, 15, and 10. These are the minimal distances. We will average them together, so we get 10. And now if we take 100 divided by 10, we will estimate that there are 10 people standing in the line, which is the perfect answer. But, of course, this example is made up, so don't try this at home, yes? But as you can see, there is a strong connection between the k value and the errors that you can get. So you can see that as you are taking larger k, so you have more elements on your sample, the error drops significantly. Now, it makes sense if you think about it, because larger k means more elements on your set, so you are getting more accurate. But of course, the problem is that more elements also means that you use more storage. So you should really balance between the accuracy requirements and the storage requirements. But surprisingly, you can see that even for relatively small k's, like 32,000 here, you are getting an error which is less than 1% for most of the times, which would be really good for most of the use cases. OK, that's all from me. And now please welcome Itai to the stage. Thank you.
Hi. So Yakir told us about the Theta Sketch algorithm and how it works, but we needed a practical working solution, right? So after some research, we found out about Druid, which is a very fast, highly scalable columnar data store. But let's see what does that really mean. Just to give you a basic understanding of which companies are using Druid in production. So you can see there are companies of all sorts, all shapes and sizes, like Airbnb, eBay, the Israeli Apps Flyer company that helps us initially with Druid, and other companies. Why is it cool? So it can store trillions of events and petabytes of data. It can serve analytic queries in sub-second, which is what we need. It's very scalable and cost-effective. And it has a decoupled architecture. So for example, the ingestion layer is separated from the query layer, as opposed to what we've seen in Elasticsearch before. So the first thing you need to know about Druid is it's a time series database. So it partitions the data first and foremost by some kind of timestamp column, like this timestamp column in the example behind me. Other types of columns are dimension columns, like this attribute column over here, which is basically a stream column you can filter your data by. And the third types of columns are metric columns, like this device ID, where you can perform aggregations and calculations on your data. All those types of columns comprise of what Druid calls a data source, which is basically an equivalent to a table in a relational database. The second thing you need to know about Druid is it has a very powerful feature that's called rollup. So if you think about it, we don't really care about the raw data, right? Like the raw events in this upper hand table. What we want to know is the aggregated data. So what Druid does, and it does it on ingestion time, when you ingest the data, it basically aggregates the data based on the predefined columns that you set up. And what we get after the ingestion is a more compact outcome, which is relatively similar to a key value store, right? So you can see in this example, and this is the example for the simple count ingestion, that I have 3 instances with attribute 111, right? So this is the raw data, and in the outcome, what Druid actually stores is the count 3 for the number of instances for this attribute for this given date. Now, it's really important to understand that it does it on ingestion time, and that gives us the benefit of when we query the data, we are getting really good results because it just needs to retrieve that row. So this was a simple count use case, but we are talking about the count distinct, more complex use case. So it does something similar. You can see that in this case, the raw data is the same. But now what we do is we use another type of aggregation that's called Theta Sketch aggregator. And you can see that this device ID right here appears twice. So what Druid stores at ingestion time is this device ID repeats itself twice, and there's another device ID that appears only once. So Druid stores the number 2 because there are 2 distinct devices. Now, Druid doesn't actually store the number 2 because I mentioned, Yakir mentioned earlier, that we want to do set theoretic operations on the data. So for example, I want to know how many unique devices have gotten attribute 111 and attribute 222. And I can't actually union or intersect the number 2 and the number 1 because it's meaningless, right? So instead, what Druid actually stores is something that's called a Theta Sketch object, which is, you can think about it like an array of samples that we've taken from the initial set. And what it needs to do in real time is actually calculate the intersection or union between those arrays, and you can have multiple objects in your formula. And the size of that Theta Sketch object is defined by the K size, as Yakir mentioned earlier, the K from the KMV. So the number of samples affect the size of the Theta Sketch object. But the way that Druid stores the data actually allows us to do those things of intersections and unions during querying time. So let's look at Druid's architecture for a few minutes. So Druid's architecture is not simple, and it's comprised of 3 types of processes. So we have processes for ingesting the data, we have processes for querying the data, and we have processes to manage all that orchestration. If we are talking about ingesting the data, we can either ingest data in real time through, for example, Kafka into what is called in Druid real-time nodes, or we can do batch ingestion through, for example, MapReduce jobs into a component that Druid calls deep storage. Now, the deep storage is basically a scalable storage like HDFS or S3 in our example, because we are running on AWS. So the idea of doing that in batch, which is what we do, is that you don't affect the query at all because you ingested the data through MapReduce job into deep storage, S3 as I mentioned, and you didn't ingest data into the Druid cluster itself, so no effect on the query. But you probably ask yourself, okay, so the data is addressed on S3 or on your HDFS, but we still need to make it available for queries. So what happens is there's a second set of nodes that's called historical nodes, basically holding the historical data, which in the background pull the data from the deep storage into their disk and memory and make it available for queries. Now, the query layer works that way. We have a client that wants to send a query. Druid supplies a REST API for querying the data. So the REST is sent over to a third type of nodes that's called broker nodes. Those nodes basically get a query, parses it, and pass it along to either the real-time nodes or to the historical nodes that hold the relevant data. Once the data gets back from those nodes, the broker nodes need to do the final aggregation and return the result to the client. So that's how querying works. Now, as some of you might identify, this is basically an implementation of the Lambda architecture. Let's see how we use Druid in production. So Yakir mentioned we have a central Kafka on AWS, and from there we have Spark applications doing basic transformations, and from the raw events, we get tuples of timestamp, attribute, region, which is, in our example, a country, and the device ID, and those are written to S3 in the format of Parquet files. From there, we have MapReduce jobs. Druid supplies those MapReduce jobs built in. So you just run MapReduce jobs on top of your input, and the MapReduce jobs do the ingestion do the aggregation, sorry, on ingestion time. And what we have in the deep storage right here are basically binary files that Druid can read into the cluster and make them available for your clients. In our example, the Nielsen Marketing Cloud SaaS application. To show you a comparison between Elasticsearch, as Yakir mentioned earlier, and Druid in terms of query performance, so you can see that in Elasticsearch, as the number of concurrent queries went up, the average response time went up even faster. As opposed to Druid, at least in initial POC, where you can see the average response time is quite constant. Now, of course, if you're running thousands or millions of queries per second, you'll probably see a slight aggregation, right, in query performance, but it just goes to show you how Druid handles those types of queries. So this is how we use it, and now what we want to share with you is our pains and provide you some guidelines in order to make your journey with Druid a bit easier. So setup isn't easy. I've shown you a few components in Druid's architecture, and it's not even all of it. So it took us a few months to get to a production deployment. Luckily, there are online resources you can use, like Druid's documentation and other things, in order to help you set up your production cluster. We actually wanted to give you a real-life example from one of our production clusters and show you how it works for us. So in this use case, we're talking about deep storage, as I mentioned, on S3. The number of data sources or tables, like I mentioned earlier, is under 10, and they are all using those types of Theta Sketch aggregations. The size of the data, the aggregated data on the cluster, is over 30 terabytes. We're talking about around a year of data. And for worker nodes, we're using the type of nodes that are memory-oriented. I'm not sure how many of you are familiar with AWS types of instances, but basically those are R48XL. But even if you're not familiar with those types, you can see we're talking about 32 cores and 244 gigabytes of RAM per machine. This is for the broker nodes. For the historical nodes, what we use is another set of nodes. Those are i3 8XL. But the thing here, and I'll touch it a bit later, is they are not only heavy on memory, but also using very fast NVMe SSD disks. And it's important, and we'll see it in a minute. OK. Another thing you should really do, as with any other system you have in production, is carefully monitor it, right? So Druid is very verbose, and it can emit a lot of metrics and let you see what's happening inside your cluster. So what we are doing is Druid has a built-in support for Graphite, and probably some of you are familiar with it. And we're using a service that's called Hosted Graphite in order to ingest all those metrics and show it up in dashboards. And this is an actual example from one of our production clusters. And what you can see here that around 6 p.m., we had a spike in the query time, right? You can see that right here. So if Druid wasn't verbose enough, you won't be able to understand what's going on. But as I said, luckily, it is verbose, so you can see and you can investigate other metrics and understand what's going on. So in this particular example, you can see a correlation between the spike in the query time and another metric that's called pending segments. I mentioned earlier that Druid needs to load the data into disk and memory in order to serve the queries. So pending segments means that Druid, in order to provide the data for the relevant query, had to pull the data from disk into memory. That's the basic concept behind pending segments. So you can see, because for this specific query, it had to load, or specific queries, it had to load a lot of data into memory, then it took more time to serve the query. This is exactly the reason why we switched at a later phase our instances to use very fast SSD and NVMe disks in order to mitigate this issue. So data modeling, I guess all of you are familiar with some kind of databases, right? So any database, you should really model your data based on what you need to use it for. So I'll talk about two options here. So Yakir mentioned that for the Theta Sketch set theoretic operations, we've encountered the problem of intersecting a very large set, for example, all devices from the US, with a relatively small set like, I don't know, those are interested in Porsche, okay? So for this example, you might get a very high error rate. And this is what we had. So initially, our data model was a column for timestamp, a column for attribute, and everything was an attribute. So Porsche intent was an attribute, US was an attribute, you name it. And the count listing is basically the metric column I mentioned earlier. And again, if we wanted to know how many devices are from US and has Porsche intent attribute, we needed to intersect these two rows. Now, in order to mitigate this problem, what we did is we extracted all the regions from the attribute column and created a new column that's basically called region. And now if we want all devices from US that are interested in Porsche, we don't need any intersections. We just need to retrieve this specific row, right? So obviously, this doesn't solve all use cases of the set theoretic operations problem, but it gives you an idea of how you can mitigate similar issues. Another thing you can do is have different data sources or tables for different use cases. So for example, if you need very, very fast queries, and you can tolerate a bit of lower accuracy, what you can do is have data sources with relatively low K, like say K equals 4,000, okay? K from the K and V Akir mentioned. And you'll have very fast queries, maybe a little less accurate. On the other hand, if you need queries that are very, very accurate, but you can tolerate the penalty on the query performance side, then you can have a very high K, for example, 64,000, and your queries might be a bit degraded in performance, but you get much better accuracy. So it all depends on your use case. Query optimization. So I mentioned that Druid supplies a REST API where you can send your queries over and get the response or the result of the query. So we found out that if you combine multiple queries into a single query over that REST API, in average, you'll get better query performance. Another thing you should do is use filters. So filters basically like your every where clause in your SQL statement. So obviously, you need to use those in order to get better query performance. And the last thing I'm going to talk about here is the type of queries you need to use. So with SQL, you have, if you need to group your data by some columns, you just use the group by clause. In Druid, you have two options. If you need to group by group your data by any arbitrary column, you can use the group by type of query. But if you need to group your data only by the time series column, then you should really use the time series query because it's very efficient in resource consumption. Your queries will be much faster. Okay, let's talk about cost reduction for a while because it's very important probably for all of you and for us because we run on cloud and we pay as we go. So we use batch ingestion, as I mentioned, and we had a relatively large cluster, 140 nodes cluster, in order to run those MapReduce jobs that ingest the data into the cluster. So what we've done is we switched 85% of them to run on spot instances, which is basically equivalent to Google's preemptive nodes or something like that. And we were able to reduce the cost by around 80%, which is a huge cost improvement. Another thing we've done is initially what we've used for the POC with Druid is CSV input format in order to ingest the data. Now, once we switched into the Parquet columnar format, which is obviously much more efficient, we were able to significantly improve both the ingestion time and the storage we use. And the last thing about that is how we do the batch ingestion. So I mentioned earlier that we read the data from Kafka using Spark, doing transformations, writing the data to S3, and from there, we have MapReduce jobs that ingest the data into Druid. So my colleague has a very interesting idea of pre-aggregating the data in the Spark application. So by either using the group by, and sorry if I had code in the presentation, but either using the group by or the combine by key operations within Spark, we were able to significantly decrease the output of those applications, and we're able to significantly reduce the number of nodes we use for the MapReduce clusters during the ingestion. So we are talking about over 2 million savings yearly just by doing this optimization. So community, and I'm very happy about that because the Druids community is very active, it's very helpful, so I really encourage you to check the online resources like the Druid documentation and the Druid Google groups to help you with what you're doing with Druid or to get started if you haven't started yet. Some things about future work. So we are researching for more ways to improve the intersections of small sets and large sets, as I mentioned earlier. We are researching for ways to further improve query performance. We are exploring the option of tiering. That's the way Druid calls it, tiering query processing nodes. For example, reporting vs interactive queries or hot data vs cold data, and obviously version upgrades. So what have we learned? So answering counting questions in real time is a challenge, right? So luckily, approximation algorithms for the win here. We learned that Druid provides a concrete implementation of the Theta Sketch framework, and it's a columnar time series database that can store trillions of events and serve sub-second analytic queries. It's very scalable and cost-effective and used widely among data companies, and it can be used for both the distinct count queries via the Theta Sketch or for simple counts. And some words of wisdom for us. I mentioned that setup isn't easy, but you have online resources to help you. That ingestion has little effect on query, which is very important for us, using the deep storage component. We learned that Druid provides very good visibility, and we've learned that you can improve your query performance by carefully modeling your data. Just before I wrap things up, a few things we care about. So Women in Big Data, we are currently building the Israeli chapter of Women in Big Data, and it's a worldwide program that aims to inspire, connect, grow, and champion success of women in big data. And they have a website, and there's actually a Women in Big Data launch today at 12:30 p.m., so I invite everyone to join. Tomorrow, I'm going to talk about different streaming methods with Spark and Kafka at 2:50 p.m., so you're all welcome to join. And also, we have a very, we try to make it active tech blog where we share the interesting things we do on the Nielsen Marketing Cloud. That's it for me. I thank you for your time, and I'm opening up for questions if you have any. Yeah?
Hi, I have a couple of questions.
Yeah, sure.
So we have our own private data center, right? So we're not on AWS or Azure.
You have your own data center?
Yeah, so as in my company, we have our own data centers.
Yep.
And we don't have these kind of large machines that you talked about, right? So is it possible for me to set up Druid and, by scaling the number of nodes, but reducing the size
of the node?
Spec of the node.
Well, it really depends on the use case. So if you need Druid for the simple counts use case, then the answer is yes. For Theta Sketch, and really if you need very high accuracy, then you really need machines with more memory. But I guess you can do some kind of balance. I mean, I wouldn't take a machine with, 8 gigabytes of RAM for serving everything. Sure. But I guess you can do it by carefully tuning your system.
For example, you mentioned 244 gigabytes memory. Yes. So we can go for example, say a 120 gigabyte machine, but double the number of nodes. Or does the performance impact get impacted with such kind of configuration?
I believe you can do it. The basic answer is yes, but in terms of specific, you probably need to. It really depends on if you do it on a daily basis, on maybe an hourly basis. It's hard to give an answer, but basic answer is yes.
Two more questions.
Yeah, sure.
Yeah. Okay, so does Druid provide queries across data series, data sources? Because you mentioned in data modeling that
that's a good question. Yeah. So just to repeat it. The question was, does Druid provide queries over several data sources? And the answer is no. There are no joins in Druid, so you can't join several data sources. The only I would say feature that's relevant for that is if you need to use lookups, right? If you store, for example, if the attribute is stored as a numeric attribute, and you have some kind of string data dictionary, then you can do that in Druid. You can have the numeric attribute and have some kind of external lookup and join them to present it in, for example, your real-time dashboard. Okay.
And finally, say if you're running some sort of Spark microbatch, and that's a real-time ingestion. Say you use Kafka and create maybe a Spark microbatch of say few seconds, and then ingest into a real-time node. Yep. In this particular flow, is it possible for us to create the theta, the count means the KV, the Theta Sketch object in the Spark application, and then ingest that object onto Druid?
Okay, it's an excellent question. So yeah, just to repeat it. So the question is, can I actually create the Theta Sketch object myself in the Spark application that reads the data from Kafka? And the answer is yes. We're actually doing it not for the real-time through Kafka to the real-time nodes, but we're doing it in the, that's how we actually managed to reduce the time for the batch. So we are using Theta Sketch for the batch. I'm guessing you can do the same for real-time. I need to, need to check the doc, but I'm guessing you can do the same. Cool. Yeah. So you and then you.
Thanks for that talk.
Thanks.
This was really great, and I would put 1,000 of likes. that setup is not easy. We struggle to a lot of users. So the question is about improving data accuracy when joining data sets, like small data set with large data set. How do you assess accuracy, and what's the current error rate for you?
Okay, I'll just repeat the question. Maybe Akir can answer it better. So the question is how we can measure the accuracy of intersecting small and large sets.
Yeah, so this is a really good question. And the problem is that for Theta Sketch, there is no, like the error in this specific case is unpredicted. So what we are doing is we have this formula for try to predict the potential error. It is based on the documentation for Theta Sketch, so we give this confidence to our clients, and we tell them that for based on the use case, if they are selecting a very small set and a very big set, we tell them that this result is not very confident and they should use it carefully. But unfortunately, we haven't found like a method for saying, okay, this is the anticipated error for this use case. It's unpredictable.
Even for your internal roadmap, so you have this item to improve accuracy. So
yeah.
How do you envision, would you measure that you actually improved accuracy?
So we have two methods in order to improve the accuracy. The first one is based on a machine learning research that we are running, which is an additional optimization algorithm that we're running on the Theta Sketch object in order to improve the accuracy. This is very initial work, which we don't have the results yet. The second method that we developed is to break the Theta Sketch object into multiple small Theta Sketch objects. So we are taking the very large Theta Sketch object, breaking it during the ingestion time. So once we prepare the sets for the Theta Sketch, we create mutually exclusive sets. And then we have like several Theta Sketch objects, smaller Theta Sketch objects, which we can intersect with the small Theta Sketch object. And we can also sum the result because they are all mutually exclusive. So this is a better approach that we are using. And with this, we managed to get significant accuracy improvements, and this is something that we are still developing. Yeah.
So I think we're running out of time, but we will be here, and you can contact us via LinkedIn. And thank you very much for your time, everyone. Thank you.